In this video, we're going to learn about related rates. So for this example, a square grows so that the length of its sides are increasing at a rate of 3 meters per minute. How fast is the area of the square increasing when the sides are 9 meters each? So the idea of this is we have some kind of square that's going to be growing, and as the side grows at a certain rate, the area is growing at a certain rate, and we want to relate those rates of change together, and we're saying that the sides grow at a certain rate, and we're going to freeze it right when the side reaches 9 meters, so whatever size that happens to be. So to help us out, I'm going to draw a little picture. So I've got my square. I'll label each side X. And the real question here is how fast is the area of the square increasing? So we're going to start with an area formula. So area equals x squared. So that's the area of any square. And then what the question is asking is how fast is the area changing? So it's looking for a rate of change of area. So we want to find the derivative of this equation with respect to time. So we are doing this per minutes, so respect to time. So if I find the derivative of this, the derivative of A is dA dt. That is my rate of change of my area with respect to time. The derivative of x squared is 2x. My variables don't match. It's with respect to t, and it's an x variable. So I have to tack on a dx dt, a chain rule, kind of like from our implicit differentiation. And that is how fast the side length is changing. So a couple things off on the side, dA dt, that's what they want me to find. That is how fast, that's the rate of change of the area with respect to time. That I don't know, so I'm going to find that. dx dt is how fast the sides are changing, and they tell me in the problem that the side is increasing at a rate of 3 meters per minute. And then the last piece of information, they give me when x is a specific moment. So right when that side length is 9 meters, that would be a fixed x at that moment. So I'm gonna plug those numbers into my formula and solve for it. So dA dt will equal 2 times 9 meters. That's my fixed x. And then the dx dt is my 3 meters per minute. So I'll plug that in, and I'll simplify. I'll multiply the 2, the 9, and the 3 together. So my dA dt should equal 54, and then my units will be a meter on this one and a meter on this one. That's why it becomes meters squared, and then of course per minute. So that is my rate of change of my area. The area is increasing at a rate of 54 meters per minute. So that's the first one for a square. The next one, if we're moving on, this one is water is leaking onto a floor. It creates a circular pool, so we're going to build a circle. The radius of this pool increases at a rate of 3 centimeters per minute. So that's my rate of change of the radius. They want to know how fast is the area of the pool increasing when the radius is 12 centimeters. So that's a fixed moment. So I've got my circle, radius of r, and then how fast is the area increasing. So my base formula here would be area, because that's what they want me to find, the rate of change of the area. So area equals pi r squared for a circle. I want to find dA dt, which is the rate of change of the area with respect to time. Couple things they did give me. They gave me dr dt. That's how fast the radius is changing, and that's changing at 3 centimeters per minute. And they also told me specifically when the radius is 12. So we have a 12 centimeter fixed radius at that moment. So my circle is growing, and I'm freeze framing it right when that radius hits 12. I want to know how fast the area is growing. So we're going to take our area formula, and we're going to find the derivative of that with respect to t. We can tell it's with respect to t as well because we have this per minute right here. That's my respect variable on this one. So if I find the derivative of that, derivative of a is just dA dt. Essentially it's 1. The derivative of any variable is by itself is just 1, and then dA dt, because my variables don't match. Derivative of pi r squared, I'm going to use the power rule for this one. So the 2 moves into the front, and then I drop it by a power. So that's why I get 2 pi r, and then the variables once again don't match, so I tack on a dr dt on the end. So there's my related rates formula. That formula is relating two rates together. It's relating the rate of change of the area and the rate of change of the radius. So let's go ahead and plug in our numbers here and see what we get. So 2 pi times the radius at that moment was 12, and the change of the radius, how fast the radius was changing, was 3 centimeters per minute. And I'm going to multiply those together. So multiply the 2, the 12, and the 3, I get 72. of course, pi from the formula, and you can make that a decimal if you want. Put it on your calculator. That's totally fine. And then the units for this is a rate of change of the area. Area is defined as area squared, so centimeters squared, and then per minute because it is a rate of change. So 72 pi centimeters squared per minute is how fast the area of that circle is changing. If the radius is changing at 3 and we're freezing it right at 12 centimeters. All right, so the next one here, we have a cube that's growing. So similar to the square, the side lengths are growing at a rate of 2 meters per minute. I want to know how fast the volume of the cube is increasing, specifically when the sides are 3 meters. So that's when I'm pausing the increase on that cube. So I'm going to draw a little cube here. Each side length I'll call x. You can pick whatever you want, but I'm just going to pick x. And they want to know how fast is the volume of that cube increasing. So that's going to be the formula I'll use. I'll use my volume formula, which is x cubed, or length, width, height. And so I'm going to find the derivative of that. So they want me to find dv dt. That's the thing they're having me look for. They're how fast the volume of that is changing. They give me dr dt, how fast the side length is changing. That's changing at a rate of 2 meters per minute. And then specifically when the radius is 3. So let's go ahead and take the derivative of our volume formula with respect to t. So I get dv dt, the rate of change of the volume with respect to time. And then, of course, power rule x cubed, I get 3x squared. And then multiply by dx dt. Once again, variables don't match with the respect variable and the x, so I have to tack on a dx dt, essentially a chain rule there. That's my related rates formula, and so I'm going to plug in my values for this and solve for the dv dt. So my dv dt would equal 3. X at that moment is 3 meters. So I'll plug that in for the x squared, and then multiply by dx dt, which is 2 meters per minute. So I'm going to go ahead and simplify that out. So I've got this 3, I'm going to square it, that'll be 9, and then this 3, so that's 27, and then of course multiply by that 2. And so when I put all that stuff together, I should get 54. My units here are meters cubed. It is a volume unit right here, so I do want that to be volume, which is meters cubed, and that happens because this meter is being squared, and then we have another meter right here, and so those go together to give me meters cubed for this one. All right, so there's our cube one, and the next one is a spherical snowball. So we're rolling a snowball in fresh snow, building a snow. Do you want to build a snowman? Causing it to grow so that the radius increases at a rate of 3 inches per second. So how fast is the volume of the snowball increasing when the radius is 2 inches? So we've got a couple of things, but let's go ahead and draw a picture. There's my snowball, my sphere. They want to know how fast is the volume increasing. So I'm going to use my volume formula for a sphere, and that's 4/3 pi r cubed. And they want me to find dv dt, how fast is the volume changing, my rate of change for that. And then dr dt they gave me, they said that was 3 inches per second, and then specifically when the radius was 2. So that's my fixed value for 2. So I'm going to find the derivative of this to get my related rates equation. So derivative with respect to t, dv dt, not bad there, and then I'm going to power rule that 4/3 pi r cubed. Now, when I'm power ruling this, just so you know, all of this stuff right here, this 4/3 and pi, all that's a constant. So I am using the constant multiple rule. I am really just taking the derivative of this r cubed part right here, doing the power rule. So 3 in the front, drop it by a power, and so I would get 3r squared. And of course, I canceled the 3's out. So that's my related rates formula. So the rate of change of the volume depends on the rate of change of the radius. So I'm going to plug in my values that I have. So my dv dt would be 4 pi. The radius at that moment is 2 inches. And then my rate of change of my radius, my dr dt, is 3 inches per second. So I'm going to simplify that. Square out my 2 first, multiply it by the 4 and the 3. So that for my dv dt, that should give me 48 pi inches cubed. Once again, you can multiply the 48 and pi together if you want a decimal answer, but it's going to be 48 pi. This would be inches cubed. We know it's cubed because it's the rate of change of the volume, but we can also double check with our units. So I've got inches squared and another inches right there, so that would give me inches cubed. So 48 pi inches cubed per second would be the volume of that sphere.